Thanks very much for the organizers, for Sergei, for other people who took part in the organization, informing us by electronic letters. So I'm very happy to be here in the conference dedicated to the memory of Volodymyr Sharko. So I will at first speak about personal things and then about mathematics. So we first met with Volodya. It was in the late 70s. So late 70s. There were Alexander's meetings, so in some sense it is simpler for me to speak now because many information was already told. Regularly Alexander's meetings were in Moscow. Topology meetings, there were not very many people, so we had opportunity, almost everybody, to speak with everybody. So it was late 70s. Volodya was coming from Kyiv, I was coming from Novosibirsk, so it was like, as we would say now, international conference. But real personal relations started with 79, when he invited me to the Crimea School of Conference. So it was exactly that this year it was a huge Moscow topology conference. Of course we met there, but then maybe it was June 79, so he invited me and I participated in this Crimea School Conference on topology that Sergei was mentioned in the previous talk. Of course, since this year we were speaking, meeting, maybe drinking regularly, and in particular, and that was not mentioned in Sergei's talk, last time I visited Kyiv, it was another Volodya's invitation. It was Kyiv Topology Conference in '92. And since that time, and as also Alec told, there were regular, and in particular this photo, which was made in Mias, in the lake in Chelyabinsk region, it was 99. So these were the mainly, and of course there were other conferences, for example, Rockland conference, not this year, but previous Rockland conference. Of course, there was a huge conferences, topology conferences, which were held each 5 years. For example, it was 82 conference in St. Petersburg, Leningrad Topology Conference, and then it was the last Old Union Topology Conference. No, 7. Yeah, sorry. Thanks. Yeah, because they were held each 5 years, so it's very, very simple. And maybe if I told about this, if now I remember, it was first that I participated in my life, and Volodymyr was the first 77 Minsk conference. So some items from my personal relations, which were always connected with mathematics, with Vladimir. So, and in particular, I remember this was my last visit to Kyiv. I didn't know at that time that I was in 2000. Okay. So now to mathematics. Now to mathematics, to topology, to the domain that for which we are here. So I'll speak mostly about braids from a point of view of algebraic topology. And my talk is in principle close to what I was speaking a month ago in St. Petersburg. So excuse me, Taras and Ivan, who were at my talk in St. Petersburg. But this talk here, I would like, as we have a broad conference, I would like to speak mostly about not my recent result that were obtained a month ago, but maybe more to give some impressions about braids, and I'll try to make it more general. Today we had the first talk of Professor Sato, who made a very good impression that you understand something in Floer symplectic topology. So this is my plan, but maybe a bit too much, so you can interrupt me at any point. So I'll speak maybe some general stuff about braids. So braids can be defined, of course, geometrically. You have two planes, and you consider strands which are coming from endpoints on the upper plane to the endpoints of the lower plane, and then you make concatenation, and this will give you the structure of the group. But for algebraic topologists, the most economic way to introduce braids, this is with the help of the configuration space. So let M be a manifold, or even if you want, maybe topological space. So you take the Cartesian power of the manifold, and there is a standard action of the symmetry group, just permutations in the sums of the Cartesian power. So you just permute them, and we denote by Fn the space of n tuples of pairwise different points. So you take the Cartesian power, nth power, but you don't allow that there will be the same points with different indices. So you if n is equal to 2, then you simply take away the diagonal. But if you want, you can call this as a generalized diagonal, and you delete it. This is usually called ordered configuration space. Maybe the term is bad, but I use it because everybody is using this. But real configuration space is what is, we know that the standard notation is BMN. This is our ordered configuration space, but then factorized by the action of the symmetric group. So, and this is good word, configuration, because what does it mean? If you factorize by the action of symmetric group, it seems that you consider n points on your manifold, but you don't have order. So if you consider nth power, then by definition this is ordered. So you have the first point and the nth point. But if you factorize by the action of symmetric group, you don't have this order. You just consider these n points as a real configuration. And braid group is nothing but fundamental group of these unordered configuration space, and this is the braid group. So, if you want to stay at the ordered configuration, then this is what is called pure braid group. I don't know how it may be called in Ukrainian. In Russian, it is called colored, krashené. In Ukrainian also. So, and this is a good term because when you see the strand, which starts, for example, in number I, goes to the number I itself, then you can color each strand. But if you have general braid, then you include the permutation, then the strand which starts with number I can go to completely different number, and you can't color the braid. So it's a good word, colored braid. Sometimes even now in English some people are using for the geometrical evidence of this name is colored braid. So you see that there is a evident covering that the symmetric group acts and acts regularly because we have deleted the non-regular points. This is the generalized diagonal, and we have this covering, and from the gradient course of algebraic topology, we have an exact sequence of groups. And so you see that this is a braid group, this is colored pure braid group, and the quotient is exactly symmetric group. So the classical case where Artin was introduced in 1925 was the case that n is equal to R2. You can consider this, doesn't matter. And this is what is called the classical braid group. This is the configuration of R2. You can consider R2 as a complex plane, and then you have relation of braids with complex analysis. But just for the definition, you take just n points in R2, and then you can obtain the art in presentation, art in 1925. So this is, sorry, maybe, no, I didn't draw the picture. So, but this is a standard braid. Maybe I take for a moment. Just maybe this is standard like this, and all other. This is I. This is I plus 1. So this is what is called by acting the sigma I, and the relations are evident. Because what does it mean? The first type of relations, it means that if the strands are far away enough, then you can commute the generators. This is the algebraic version of the Reidemeister move.
But the generators aren't the braids themselves, no?
Yeah, sure.
Your sigma I is just for I's strength?
Yeah, no. N is fixed. N strands, and you consider the following braid. All are parallel lines. Only I and strand with number I and number I plus 1 are involved. I goes to I plus 1. I plus 1 goes to I. This is a braid, geometrical braid. Or if you consider the fundamental group, this is just rotation for 180 degrees. Okay, so and then you have among these elements, you have the relation. So braids are they have group structure by the concatenation. For example, if you again apply this relation, then you have sigma squared, sigma I squared, and this is not 0. This is not 1. And if you add just one relation, sigma I squared is equal to 1, then you have the presentation, the classical presentation of the symmetric group, which is taught in regular algebra courses. Okay, maybe I wrote this. No, sorry. And now let us take the following elements. Maybe this is too technical, but geometrically it is simple. I wrote this for I equal to 1 for simplicity, but in principle you may have this one. So you take the number j, and then your braid goes around strand number 1, and then returns back to number j. Okay? So you see that this is a pure braid. All strands goes to their origins. They return back. So, and this is maybe technical, but just to have an impression. And this is the relations. These guys give also the generators of the pure braid group. Evidently, as I told, they are pure. But relations, unfortunately, are not so beautiful. For example, they are not homogeneous. If you remember the braid relations, they all are positive. And here it is. But this is the life. And this presentation was done by Werner Borau in 1935. So this is the presentation. Okay. Now we can introduce such a geometrical operation. You simply take away the strand of number I. So then from braids with n strands, you obtain definitely braids of n minus 1 strand. This is not a homomorphism because of the following relation. So you need to see that it goes to another place. But if you restrict to pure braid, this becomes, because we have this thing, and this is the action of the braid on the element I. The action, if you apply to a braid beta is here, then if you take a product, the corresponding relation will be almost like homomorphism. But unfortunately, this is this term. You don't come to I, but you come to I action of beta. But if beta is pure, imagine that you are now considering the pure braid. You have di here, and you have di here. It becomes a homomorphism. So this operation, this map, which is not a homomorphism for braid, it becomes a homomorphism for the pure braid group. But now we give a formal definition. What braid is called Brownian braid. Brownian braid is formally, you can write this way, but geometrically it is the following. You have a braid, you take away any, the key word here, any. You take away any braid, any strand, sorry. You take away any strand and you obtain trivial. The trivial braid, I remember, this is just n minus 1 parallel lines, that's all. So formally you can write it the following way. You can restrict to pure braid if you like to deal with only with homomorphism. So you can consider pure braid. You have homomorphisms, and this is the intersection of the n kernels of d1, dn. Or if you like, if you are algebraist, you like equations, then this is, the braid is called Brownian if it satisfies the n equation in the pure braid group. Okay? So you know this object very well because this is what I wrote down, what I mean. Maybe to explain why Brownian braid is subgroup and even normal subgroup in the braid group. So the proof may be geometrical. So you take a braid beta, sorry. You take a braid beta, you take a braid B, which is Brownian, and you take here beta minus 1. Beta is arbitrary. Beta is arbitrary group okay, so what does it mean that B is Brownian? Means that if I take away any strand, then it will be trivial. So suppose that it is done. Then I have trivial. And what I have here, I have B minus 1, beta minus 1, with one strand deleted and beta deleted. So this will be again trivial thing. So this very elementary geometric approach tells us that Brownian braids are subgroup and even normal subgroup in the braid. So what will come if you consider the braid on n strings and strands. And in the braid, there is a connection with links, with knots. So this is a procedure of closing. This is not a closure like in general topology, or closure that Marek was saying us today. But this is closure means that if you have a braid here, then you make the following thing. Each point, say you have first strand, you connect with the same point in the upper plane. And then if there was a braid here, when you make this kind of closure, you have a link. And the simplest example of non-trivial Brownian braid, if you make this kind of closure, you get the simple Brownian link. You have the Borromean link in the closure. So the object of Brownian braids is the braid analog with the help of the closure of the evident procedure of Brownian link, in particular Borromean link. Okay. Then one of our theorems with colleagues, whether no, I didn't mention, with Vladimir Vershinin and Kyiv. We have a theorem which gives a connection of the Brownian braids and homotopy groups of spheres. So this is defined a little bit algebraic object. I don't have time to detail it. Is like Novikov ring in the first talk, but it is purely algebraic object. And we have a theorem that if our manifold is not a sphere or not RP2, the manifold is not necessary to be compact. This may be better to say, you take a compact manifold and you may take away several points. The essential stuff is that the manifold should have finitely generated fundamentally. Okay. So then in all cases you have this algebraic object, and in the case of sphere S2 and RP2, when n is equal to 4, then there is the following exact sequence, and in particular, if n is equal exactly to 4, this theorem, our theorem, is valid, then you have P3 here, Brownian braids, and this is one of the Hopf relations that Marek told us today. You have here the Hopf element of the S2, P3 of S2, which is obtained by complex stuff that you taught us, right? The complex projective space and Hopf values. So the first, maybe the first example of homotopy groups of spheres, it was Hopf example, which was published in 1935 also. In some sense, there is a Brownian braid. But in spite of this theoretical result, there is no chance to characterize these braids, which is mapped. So our proof comes from algebraic topology. So no chance to find and rewrite, but no, at the moment it is not known present geometrical description of the braid of RP2, which is mapped to the Hopf value. Okay, this is the theorem about quotients. As I told that these groups are normal subgroups, so the question is about the quotient. We know that they are finitely presented groups. So, excuse me, how many minutes do I have? 5. Okay. Then I skip it. This is the coin braid. Or maybe I describe this, which is essential. Okay, maybe I'll say. So, if we now have a generalization for Brownian, we have 1 here, and now just have another equation with constant term. So it is possible. And in particular, one type of elements is what is called Garside element, who was defined for the solution of the conjugacy problem in the braid group. This is called like this, but maybe geometrically it is the following element. It is a plane, this is original picture of Garside. So it is obtained the following way. You have a frame of n parallel, the trivial, and then you make rotation by 180 degrees. And you have this. So you 180 means c over 2, excuse me. So it means that 100 means that this goes to opposite. Exactly what happens with 100. It is not pure. The example is that it is not pure because this goes. But pure, you can obtain delta square when you make rotation of 360 degrees. You have pure braid. And by the way, this will be the center of the braid group. Okay, this is our results about this generalization. We call this object coin braids, that they satisfy the following equation. We generalize. This is technical stuff, how we prove these. This is technical stuff. Sorry, I skipped it. And we have results. Okay, this is my colleagues from Pedagogical from Novosibirsk and Jibu from Singapore. Probably I skipped this, but maybe I say just some words that for any group, there is a standard procedure that you can take the descendant central series, which is defined by the commutators, and if you consider the subsequent factors, you have the structure of the Lie group over Z. This is because of some commutator relations in a group. Okay, this is this very interesting result.
This is direct sum of those. Yeah.
Sorry?
Lie group is Lie graded algebra.
Lie algebra? Yes.
It's defined as a direct sum of L i's. Yeah?
Sure, absolutely. So this is the yes, but is graded. You consider as graded object. This is in each stage is the following. If you like, you can take direct sum. Sure. Okay, and the wonderful result, which was obtained several decades ago, this is the result of Toshitaki Kono, who calculated the Lie algebra for the pure braid group. That's why I made the pictures of the elements Aij, but small aij. This is their images in the Kono algebra. So because you take this element in a group and the corresponding element of the factors and so on, and there are very beautiful Lie algebra structure. So I just showed you the relations for the pure braid group. Remember how they were non-homogeneous and rather complicated. If you linearize them, then this is the Conan algebra you have, so beautiful. So you have plus instead of multiplication, you have these structures as the commutators. So this is the. So what are our results? So this is what are our results? Okay, so maybe first of all my results about the following, the analog of the Toshitaka Kono result on classical pure braid group for the pure braid group on surfaces, but in coefficients, Lie algebra structure for the so it was obtained by Dragomanov, but by the methods of algebraic geometry, and he calculated the corresponding Lie algebra, but over C, and it can be reduced to rationals. And my result is that this is the Dragomanov relation, and my result is that these relations are true for Z. There is it's not essential that complex numbers are rational. And okay, and the proof is based on the results of Ihara on braid groups. Ihara, Kaneko, Nakamura, and okay, and sorry, yes, so this is technical. Maybe as an example, the result of what we have in the case of torus. So this is the Lie algebra for the torus, the simplest way. So we have because torus have braid groups of torus of surfaces. So I need to finish, or 1, 2 minutes, 3 minutes. Yes, okay, of course, lunches. Just I finished with one phrase. So in general, you see that this Lie algebra is much more complicated than Toshitaka Kono's algebra, but in general, what is happening when you consider braids on surfaces? So if you consider just braid on one string, on manifolds, this will be fundamental group of the surface. So fundamental group is included by definition to the braid group. So braid group in surfaces, this is the marriage of the fundamental group of a surface and the braid group of a plane, but they are connected not trivially. And so this results, you see that this is how there are generators C and D, which correspond to the fundamental group of the torus. So thank you very much for it.
Not only one. So first, my question is, do you think it's possible to extend your result for non-compact surfaces?
No, these results are for non-compact surfaces.
For
the only thing is you can take, for non-compact, it is even simpler because you have surface, you just take away one point, fundamental group will be free group. So if you deal with free group, it's simple. The most complicated case is that when you have surface group, fundamental group, which is not free, one related group.
That's
So,
a technical
yeah.
compact.
And I mentioned compact case because they are mostly complicated.
Okay. And could I ask more? Yeah, but what about the nipotence of break group and the quotient of by Brownian group? Do there chance do you look for nipotence of the group?
No, the only thing, and it is not very simple, the only thing that we can prove that this is the finitely presented group, that's all. But here, for example, the pure break group, they are not, they are in some sense nilpotent in limit. So they have the central series goes to infinity, but the intersection of all is zero, is one.
Okay,
So the nilpotence on infinity.
The third one, but the last one. So the just a remark. So I think you know that there is some result by Gonsalves and Watsky about the break group of surfaces.
Yeah.
But I think it was your talk is related to this, but I don't know if I mentioned about Brownian. But something by that is there.
Very good question. I just explored your question, and look, I skipped it. You remember?
Okay, good. Thanks a lot. Sorry,
I'm using the results of your friends in the group.
Sorry.
Yeah.
Как вы это сам